Hello everyone, I am Timon Hartwig, the first author of this paper with the title Public Release of A-SLOTH, in which we present our semi-analytic model, A-SLOTH, which you can use to simulate the formation of the first stars, first galaxies, second generation stars, extremely metal poor stars, or Milky Way dwarf satellite galaxies. In this brief video, I would like to give you an overview of what A-SLOTH can do and how you can use A-SLOTH to do science. So A-SLOTH is a semi-analytic model that is based on dark matter merger trees. So you can think of A-SLOTH climbing the merger trees. The merger trees are dark matter halos and how they merge hierarchically over time. And so on top of this dark matter skeleton, we model the formation of stars and we model their radiative, chemical, and mechanical feedback over time. Now, there are many subgrid models in A-SLOTH, input parameters, and we have like a 10-page section on the methodology that you can please have a look at if you're interested. To summarize these, I would like to show you the following figure 3 in the paper, which shows the baryonic evolution in one of the branches. So specifically, here we see time after the Big Bang in megayears. The top panel shows masses in solar mass, and the bottom panel shows metallicity logarithmic relative to solar. So it's a busy figure, but let me show you what rich information is available in A-SLOTH and that can be used for science. The input, if you want so, is the green line. The green line here shows the halo mass. And this we have in a resolution of 5 to 10 megayears. So here you see the steps. And this tells us what kind of halo we have and how it grows in mass over time. But the actual job of A-SLOTH is happening down here when we look at the baryonic components and what they are doing over time. So here we're looking at the main branch, so one branch in the merger tree. And for example, we trace the hot gas and the cold gas, so here in red and blue, and then how stars form. Here pop3 stars in orange and pop2 stars in light blue. And you can see at the very beginning, there are no metals. The metallicity is minus infinity. And we only start with hot gas, the red one, which then slowly cools to cold gas, the blue gas, which then becomes gravitationally unstable and forms stars. So here at the beginning, we form metal-free population 3 stars in orange. These massive stars at some point explode as supernova, which are here these olive yellow points. So here we inject metals and energy, and the energy will evacuate the remaining gas in the halo. And then it takes some time, a few tens of megayears, until we can re-accrete first hot gas in red and then convert it to cold gas in blue, until we have enough cold gas and we can form metal-enriched second generation stars, here in light blue. And also those at some point explode as supernova. They produce metals, they eject remaining gas, and the cycle starts again. So as I said, this is just one branch of the merger tree, which does not necessarily have to be representative for all the physics, but it's quite representative of the methodology inside A-SLOTH. So this shows you what effects we include, how the baryonic gas components evolve over time, and what information is available inside A-SLOTH to investigate some scientific questions. In A-SLOTH, we also have various free input parameters that need to be calibrated. To calibrate those, we have 6 independent observables. So these 6 observables are the ionization history. So in a cosmologically representative box, we try to reproduce the optical depth to Thomson scattering, which you see here. Then we use the stellar mass of the Milky Way and the distribution of masses of its satellite as 2 calibration constraints. You see the distribution of the cumulative satellite stellar mass function here. And we use extremely metal poor stars. So we use extremely metal poor stars and their ratio to ultra metal poor stars. And we use the ratio of extreme metal poor stars to all stars in the Milky Way. So these two ratios are two additional observables. And we use the cosmic star formation rate density at high redshift, specifically between redshift around 5 and 10, because that's where we have overlap between observations and our cosmologically representative box for A-SLOTH. Our calibration strategy, we discuss it in more detail. We have developed a method that we call the gradient descent. It's a combination of gradient descent and an iterative one-dimensional calibration. So we have various one-dimensional calibrations iteratively after each other. With all this, we eventually find an optimal fit for our input parameters. So here you see the 9 free parameters in A-SLOTH. Those 3 we have fixed from the beginning because we can motivate their values, or the values doesn't affect the results very much. And these 6 parameters we have explored during the calibration, and we found a best fit so that we can reproduce all the 6 observables equally well at the same time. And while these parameters are very good at reproducing the observables, we do not necessarily claim that these are the only best parameters, because, for example, the maximum mass of POP3 stars, we would suggest 210 for a good fit, but that does not mean that we claim that the maximum mass of POP3 stars needs to be 210. So in a future study, we want to explore the uncertainty ranges of these parameters, which A-SLOTH would also allow. And now that we have a rough overview of what A-SLOTH is doing and what A-SLOTH can be used for, let me summarize the advantages of A-SLOTH compared to other models in the literature. So first, A-SLOTH is now public, so it can be used by everyone. The source code is transparent, so you can see what is going on. And A-SLOTH uses either EPS-based merger trees as input or merger trees from n-body simulations, so from dark matter-only simulations, which allow spatial information to be used in the feedback model. A-SLOTH is very efficient and parallelized. So we have optimized the memory allocation, we have parallelized it. And when you download A-SLOTH the way it is and use the EPS mode, you can run it in 1 minute on your laptop. If you want to use a cosmological representative box, even this runs in just a few minutes on a decent computer. Then in A-SLOTH, we sample individual population 3 and population 2 stars. This is especially important for the stochastic supernova feedback in small galaxies and to sample extremely metal poor stars in the Milky Way, because then we can really follow the single individual enrichment from supernovae of individual stars. We track individual elements with A-SLOTH. So in the fiducial model, we trace carbon and iron, but you can extend this and trace the elements that you are interested in. A-SLOTH is calibrated, as I said, on 6 independent observables from the local universe, the Milky Way, and the high redshift universe. And we reproduce various additional observables, such as the recovery time distribution function. We have a subgrid model for inhomogeneous metal mixing. And this was the main, these were the main features of A-SLOTH. So I hope I could convince you that A-SLOTH is a versatile model to study the first and second generation of stars. Please let us know if you have any questions, if there are problems, or if you have ideas to collaborate on. Otherwise, happy coding. And we also link the tutorials where you can then see how you can get started using A-SLOTH. Thank you very much.